Hello everyone. Let's start with the question practice session for NEET 2025. Today our topic is GOC part 2. Part 1 has already been uploaded in the channel. Subtopics for today are isomerism and electronic displacement in covalent bonding. The questions that are selected for today's session is either NEET PYQ or similar questions like the NEET PYQ. Okay, let's start. Fine. Here, the first question that is asked is, which of the given compounds can exhibit tautomerism? Tautomerism. What is tautomerism? If we say ketoenol tautomerism, what is the necessary condition? This is the ketonic group. Alpha carbon with respect to the ketonic group must be sp3 hybridized. This is the first condition. Next is the alpha carbon should contain at least one hydrogen. Okay, this is another condition, that the alpha carbon should contain at least one hydrogen. Right? Now what happens here? The pi electron density is pulled by the oxygen. To fulfill this, the carbon hydrogen bonds shift over here, and finally what we are getting? This is O negative double bond and CH2, the hydrogen goes out in the form of H positive. Now, due to the high electron density on oxygen, it pulls the H positive towards itself, and we are getting a OH here with a double bond CH2. So, because we have this OH functional group here, we call this as enol form, and this one is the keto form. This is the keto form, and we call it as ketoenol tautomerism. If we number this, now this numbering is not based on the IUPAC numbering. This numbering are for the systems of tautomerism. Okay, so do not get confused with IUPAC numbering. So if I number it, the oxygen is numbered as 1, this carbon as 2, and this carbon as 3. The sp3 hybridized alpha carbon as 3. Shift of hydrogen takes place between these 3 atoms. Hence, this kind of tautomerism in the system, we also call it as 1, 2, 3 system. This is also a 1, 2, 3 system in which the ketoenol tautomerism is happening. Now, we also say ketoenol tautomerism in other systems like 1,5 system. What is 1,5 system? Let's see. If I have a keto group like that, and the alpha carbon is not sp3 or there is no alpha hydrogen, any one of the condition is not satisfying, right? So in those cases what will happen? So now if I see the system, it is what? 1, this is 2, the third carbon is not sp3, this is sp2. Here also third carbon is sp2. So this carbon will not be able to undergo ketoenol tautomerism. We'll go ahead and go to the fourth carbon, fifth carbon. Fifth carbon, if you see, is sp3 hybridized. Also, the fifth carbon is having hydrogen. So in this case, what happens? Ketoenol tautomerism happens in this way. The pi electron density is pulled over oxygen. This pi electron density comes to satisfy the carbon's electron deficiency. This sigma bond of carbon hydrogen shifts here. So finally, what I am going to get as, this is the bond arrangement which has taken place. O negative, here 1, it is not affected, this carbon hydrogen bond got shifted, so here is 1 hydrogen and H positive. Obviously the high electron deficiency on oxygen pulls this H positive towards itself. Finally what I am getting here? A phenol. Finally I am getting a phenol, OH. So this is the enolic form, enol, and this is the keto form, right? So here this system, because it is taking place between 1 and 5, so we call it as 1,5 system in which the tautomerism is taking place. Fine. With these concepts, let's solve the question. So it can take place in 1, 2, 3 system also, 1,5 system also, even 1, 2 system also. Let's solve the question which is given, which can exhibit tautomerism. Now for the first case, if I see the functional group with respect to this, if I start numbering, So this is first, this is second, this is third. Third carbon, what you see is sp3 hybridized. Also it contains alpha hydrogen. Fine. So here ketoenol tautomerism is possible. In the second case, if we see, second case, if I number, how? 1, 2, 3. Again third carbon, sp3 hybridized, also contains alpha hydrogen. So here also ketoenol tautomerism is possible. Right? In the third case if I see, this is the system. If I number it, 1, 2, 3. The third carbon is sp3 hybridized, but there is no alpha hydrogen present. So this condition is not satisfying. Other side, if I see the third one, this is sp2. Again condition doesn't satisfy. So we'll go to the next carbon and check. Fourth one, fifth one. Fifth carbon, if you see, it is sp3 hybridized as well as hydrogen is present. So in this we see that 1,5 system type of ketoenol tautomerism is occurring. So all the three can undergo ketoenol tautomerism. First two can undergo 1,2 ketoenol tautomerism, and the third one can undergo 1,5 ketoenol tautomerism. So the first two is 1, 2, 3. Third one is 1,5 ketoenol tautomerism. So my answer for this is C. All of the above, that is 1, 2 and 3. Next one. Match the following columns. So this is given. The first molecule is CH3. CH attached to this is a CH3 group and another CH3, and the second is butane. What is butane? CH3, CH2, CH2 and CH3. This is butane. What difference do you see between both? First one is propane, 2-methyl propane. Second one is butane. So 4 carbon in the main chain and 3 carbons in the main chain. Molecular formula is same, but carbons in the main chain differs. So chain number is differing. This is a type of chain isomerism. A should be S. Only one AS is present, so obviously the answer is A. You can check the others also. Like for the second case, but, both are but, 1 butene, 2 butene. But means 4 carbons, but ene, that is double bond, is present on the first carbon. In the second case, double bond is present on the second carbon. So double bond's position is different in position of the double bond. So this is a type of position isomerism. Third one, what is there in the third one? Diethyl ether. Ethyl group CH3, CH2O, another ethyl, diethyl, so CH2 and CH3. This is diethyl ether. What is the next one? Methyl propyl ether. There is a methyl group and there is a propyl group. What is propyl group? C3H7. So now what difference do you see here? Around the bridging ligand, if you see the group here, ethyl groups are present. On the other side, if you see, one side methyl group, the other side is the propyl group. Groups around the bridging functional group is different. Right? This kind of isomerism, we call it as metamers or metamerism. Then group around the bridging functional group should be different. Next one, what does it say? Dimethyl ether and ethanol. So if you see, functional groups are different. One is ether, one is alcohol. So both are different functional groups. So finally we call it as functional isomer. So with the first itself we can solve the question, but remaining we have checked. Done. Third one, which of the following will have a meso isomer? Meso isomer. Before going to that, let's understand what is a meso compound. What is a meso compound? Meso compounds are generally optically inactive. They are optically inactive. Why optically inactive? They are optically inactive because of the presence of center of symmetry or plane of symmetry. In them we have center of symmetry or plane of symmetry, although there are two or more chiral centers. There are chiral centers, but because of plane of symmetry or center of symmetry, they are optically inactive. So these are the two criterias which we have to take care, that is chiral center plus optical inactivity, that is plane of symmetry or center of symmetry. I have to take care, then only we'll get the answer. First is 2,3-dichloropentane. Pentane 1, 2, 3, 4 and 5. 2,3-dichloro. Second position and third position we have chloro group, right? This is CH2 and CH3. Do we have chiral centers here? Yes. One condition, chiral center, okay. Do we have plane of symmetry or center of symmetry? No, we don't have. So this will not show any optical meso isomerism. Okay, this is optically active, so this is not a meso isomer. Next one, dichlorobutane. Butane. This is but. Dichloro, Cl, Cl, H and H. Do we have chiral centers here? These are chiral centers. One condition to satisfied. Next condition. Do we have plane of symmetry or center of symmetry? If I divide the molecule in this way, that is, put a mirror here, can you see one half of the molecule is just the mirror image of the other half, right? So this is plane of symmetry. So plane of symmetry is also present, plus chiral carbons are also present. Both the conditions satisfy. So this B option will be the answer, that is, it can form a meso isomer. Fourth one, which of the following compound will show metamerism? Just now we have seen what is metamerism, that around the bridging functional group, both the groups are different. Just now we have seen here. So around the bridging functional group, both the groups should be different. Let's check. What is the bridging functional group here? Ketone. If I bring one CH2 this side, what I'll get? C2H5 CO CH3. This is the same molecule, so this will not show any metamerism. Next one, if I bring one CH2 group here, CH2 group if I shift here, what I'll get? C3H7 S. Here what I'll get? CH3. Can I get? Now if I see both the sides, here what we have? Ethyl, ethyl. On the other hand, I have propyl and methyl. Around the bridging functional group, both the groups are different. So this type of isomerism we call it as metamerism. My answer will be B. Done. Next, geometrical isomerism is not shown by. What is the criteria for geometrical isomerism? My first criteria for geometrical isomerism is restriction in bond rotation. Restriction in bond rotation. Why restriction? Due to presence of double bond. Second condition is around the double bond, the carbon which is present attached to the double bond, around them the group attached should be different, not same. The group attached should be different, not same. This is the second criteria for geometrical isomerism. Okay, restriction in bond rotation and the group which is attached around the carbon attached to the double bond should be different. So let's understand. This is the double bonded system, double bonded carbon, right? Around this I have to see the groups which are present. One group is CH3 which is present, another group is CH3CH2, okay, methyl and ethyl. Similarly, one group is CH3 on the other side, another group is CH2CH3. For those who can't understand, I am making it here itself, right? So one of the group here if you see is CH3, the other group is CH2, CH3. So both the groups are different. One is CH3, the other is CH2, CH3. So both the groups are different. So it will show geometrical isomer. Done. So this is not my answer. Second case, this is H, the other group is C2H5, different. Again, this is H. What is the other group? The other group is CH2I. Groups are different. So this will also show geometrical isomerism. Done. In the third case, if I check, this is the double bonded carbon. Around the double bonded carbon, both the groups are same, CH2. Means, what I am saying, if I take this double bonded carbon, around this we have H2. Both the groups are same. This will not show geometrical isomerism. So your question was which is not showing geometrical isomerism. So your answer will be C. C is not showing geometrical isomerism for 5. Done. Next one. How many chain isomers are possible for C6H14? We only have to see the chain isomers. Fine. Let's see how many chain isomers are possible. So this is type of CnH2n plus 2, that is alkane. Right? Means all are single bonds which are present, alkane. So let's try to make CH3, CH2, 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 CH2 and CH3. Hexane. Okay. Next, if I make 5 carbon in the main chain, how? CH3, CH2, CH2, CH and CH3. 5 carbons, 1 more carbon I'll attach as a branch. Okay. Now, can I change the position of this CH3 from second to third on the 5 carbon chain? CH3, CH2, CH, this is CH3, then we have CH2 and CH3. See, attachment position changed, right? Molecular formula same. If I change the main chain into 4 carbons, CH3, CH, CH and CH3, remaining methyl groups I attach in the form of side chains. Remaining methyl group I am attaching in the form of side chains like this. Possible? Okay. Another 4-membered main chain if I make CH3, C, CH2, CH3 and I attach on the same carbon atom the remaining methyl groups. See? Can I make it like this? Okay. Any other possibilities can I do? 3-membered not possible. So if I alter it will be all the same. We are only talking about chain isomers. So how many we are getting? 1, 2, 3, 4 and 5. Total 5 chain isomers I can get from C6H14. So for C6 the answer will be 5. 1, 2, 3, 4 and 5. Answer will be B. Done? Okay. Next question. Next question is how many isomers in C4H10O will be? So again we'll have to find the number of isomers for C4H10O. Let's find out how many isomers are possible. So C4H10, CH3, CH2, CH2, CH2 and OH. Mind you, here they have taken all the isomers. They didn't talk about any specific type. Like in the previous, they were only talking about the chain isomer. Here we have to talk about all the types of possible isomers possible for C4H10O. Right? So this is 1, 4 carbon. Can I change the position of OH from first to second? Possible. So let's make it as CH3, CH2, CH, CH3. I put OH on the second carbon atom. Possible? Okay. Next, what else I can do? I can change the number of main chain into 3. How? CH3, C, CH3. To this, if I attach CH3 and I attach OH, can I do this? Okay. With 3 carbon atoms, can I change the position of OH? How? CH3, CH, CH3, CH2 and OH. Done. Any other possibilities for alcoholic group? Not possible, right? We can also go for ethers. So 4 carbons are there. Let's take 1 carbon on one end, O, CH2, CH2 and CH3. Possible? If I change the attachment of the propyl group and make it isopropyl. So this is methyl. I make the propyl as isopropyl, CH, CH3, CH3. Attachment only I have changed. Okay. How? Attachment was on the first carbon atom. Now I have changed the attachment to the second carbon atom. Isopropyl. Okay. I can also make it as diethyl ether, CH, C2H5, O and C2H5. This is also possible. Any other groups are possible? Okay, so how many isomers are possible for this? 1, 2, 3, 4, 5, 6 and 7. Total 7 isomers will be possible. So my answer for 7 will be C. Done. Next, a compound with molecular formula C7H16 shows optical isomerism. So the compound will be, if C7H16 is showing optical isomerism, then what will be the compound? Options are given to you. Let's see. For optical isomerism, criteria is chirality and there should not be any symmetrical like plane of symmetry or center of symmetry, right? So 2,3 dimethyl pentane. Pent means 1, 2, 3, 4 and 5. 2,3 dimethyl. Second position we have methyl group. Third position also we have methyl group. This is CH3. Okay, here H, H, H2 and H3. Do we have chirality here? Do we have chiral center? So if you see this particular carbon, okay, this is chiral in nature. So chiral center is present here. Okay, 1, we got chiral center. If we check B, so this should be optically active. Let's check the other also. If we see the B1, 2,2 dimethyl butane. This is butane, 2,2 dimethyl, CH3 and CH3. Do we have any chiral center here? No chiral center, so no optical activity will be found. 2-methyl hexane. Here also if you see chiral center will not be there. So my answer is A. Okay, because of the presence of this chiral center and no plane of symmetry or center of symmetry. Which pairs are enantiomers? What are enantiomers? Enantiomers are non-superimposable mirror images. Okay, mirror images which are non-superimposable in nature, we call them as enantiomers. So let's try to put a mirror and check whether they are mirror images or not. Okay, fine. Now if I see here, OH is present, right? This side also OH is present. So obviously this part okay. Here what we see, H is present, but here OH is present. Is this a mirror image? No. Done. Next one, OH is present, okay? On the other side OH is present. Fine. When if I put a mirror here, H is present. On the other side, what do we see? H is present, right? Similarly, if I see CH3 is present here, on the other side also CH3 is present. Similarly, if you check each of the thing, it is exactly a mirror image of one another. If I put this over the mirror image, it is non-superimposable. So we need a non-superimposable mirror image. So my answer for this will be B, enantiomer. B is forming enantiomer, non-superimposable mirror image. Next, which is more stable among the following? So few compounds are given, which is more stable, you have to identify. 1-butene, okay, double bond at the first position, cis-2-butene, trans-2-butene, and all are equally stable. All are not equally stable, we know trans is always more stable. In the most cases, trans is more stable than cis. Why? But-2-in, so this is but-2-in, CH3, trans case. So this is the structure for trans. If you see the bulky groups, these are the bulky, means bigger group are on the opposite side. So when bigger groups are on the opposite side, what we see that the repulsion is minimized. Hence, the stability for trans form will be more than that of the other forms. So answer will be C for 10th. Next one. Which one of the following exhibits the geometrical isomerism? Which of the following exhibits geometrical isomerism? You have seen the conditions of geometrical isomerism. Restriction in rotation. We have restriction in bond rotation, and also along the double bond carbon, whatever groups are present, those should be different, not the same. These are the conditions. Fine, let's check. 1,2-dibromopentene. Propene. So 1,2-dibromopropene. Okay, propene means this is propene, right? This is propene. 1,2-dibromo. We have a bromo here, bromo here. So here H will be there. 1,2-dibromo. Right? If you see the groups different, so restriction in bond rotation is also there. Different groups are also there. This can show geometrical isomerism. Next one, if I check 2,3-dimethyl but-2-in. Okay, but-2-in. This is but-2-in. 2,3-dimethyl. This is but-2-in, and methyl group is present. 2,3-dimethyl. Groups are same. Will it show? It will not show. Next is 2,3-dibromo but-2-in. This time, in place of this methyl group, if I put the bromo group, 2,3-dibromo. So bromo here and bromo here. Groups are different. This will also show geometrical isomerism. So both A and C is showing. My option is D, both A and C. Done? Fine. The compound CH3CBrClH, which is shown here, okay, is RSEZ. Which one? Now, if you see here, E and Z, they belong to geometrical isomerism. Now you know the condition for geometrical isomerism. Double bonded system should be present. Can you see any double bonded system here? No. So E and Z will not be the answer. So you can cancel out EZ. So answer will be either R or S, right? Because EZ type of system, we deal with geometrical isomers, not in this kind of cases. Fine. Either it will be R or S. So for finding RS, how do we do this? We put numbers according to the mass. Now whose mass is more out of the 4 groups attached? Bromine's mass is more, so we'll number it as 1. Next comes chlorine's mass, we'll number it as 2. Next comes carbon's mass, I'll number it as 3. Okay, so how it is going? 1, 2, 3. If I see, it goes in the anti-clockwise direction. Whenever it goes in the anti-clockwise direction, we put what? S. No, S configuration we put like that. But there is a twist here in this case. What is the twist? This H, or the lowest mass group, for this kind of assigning configuration should present in the back side of plane. How do we know something is on the back side? We put dash lines to assign on the back side. Dashed line is with chlorine, means chlorine stands on the back side of the plane, not the lowest weight group, that is H. Okay, so whenever lowest mass group is not present on the back side, that time whatever the configuration comes, we just exchange that to the other, that is R. So my answer will be R, not S, because the lowest assigned mass is not present on the back side of the plane. Right? Anti-clockwise it came. According to anti-clockwise, it should be S. But because the lowest mass group is not present on the back side, so the configuration is actually R, not S. My answer for this is A, R. Okay. 13. A tertiary butyl carbocation is more stable than a secondary butyl carbocation because of which of the following? Let's make the structure of first tertiary butyl carbocation. This is tertiary butyl carbocation. Let's make the structure of secondary butyl carbocation. CH3, CH, CH2, CH3. This is secondary butyl carbocation. How does the stability works? If I show one on one side, so this is H, H and H. How does it work? To minimize the electron deficiency, this sigma bond between carbon and hydrogen shifts. So as it shifts, finally what I am going to get? C, CH3, CH3, this is double bond CH2 and H positive. Okay, H positive is coming out. So this phenomena we call it as hyperconjugation. This phenomena we call it as hyperconjugation. So number of hyperconjugation depends on the number of alpha hydrogen which is present. How many are present? 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many hyperconjugative structures are possible in the tertiary part? 9 hyperconjugative structure. In the secondary, how many are possible? 3 alpha here, 2 alpha hydrogens here. So how many total? 5 hyperconjugative structure. We know more is the number of hyperconjugative structure, more is the stability. So what is the factor which is working? Is hyperconjugation. So my option will be C, hyperconjugation for the stability, more stability of the tertiary butyl carbocation over secondary butyl carbocation. Fine. Which is least resonance stabilized? So least resonance stabilized molecule I need to find out among the following. First is benzene. Benzene, you know, there is a complete resonance of the pi electron density throughout the ring. So highly stable. In the next case, if we see, a resonance is between the lone pair and the pi electron. This is also throughout the ring, complete resonance. Okay. And on the oxygen, 2 electron pair is there, in which only one is participating, the other is not participating. Done. In the third case, there is also complete resonance and lone pair is not participating. Lone pair on nitrogen is not participating, only the pi electrons, 6 pi electrons are participating. Okay. In the fourth case, the resonance, if we see, is in this way. It is not a complete resonance. Okay, partial resonance. We know that complete resonance is obviously having more stability factor than partial resonance. So here we see partial resonance, remaining are complete resonance. So least stable among the 4 will be the D option. Done. Which of the following carbocation is expected to be most stable? So I need to find the most stable carbocation among the following. Nitro group is what kind of group? It is a electron withdrawing group. So it withdraws the electron density from the ring. We know this, right? As it withdraws the electron density, obviously carbocation is already electron deficient. If it withdraws more electron, so anyways it is destabilizing the carbocation which is present very close to it, right? So this one is highly unstable. Again, this is also highly unstable because it is withdrawing the electron density from the carbocation center, very close. Next, out of the two, what we will see is, we know that in nitrobenzene, when we do electrophilic, suppose Y is the electrophile, electrophilic substitution, we know that nitro group is the electron withdrawing group, so it will withdraw the electron density from where? From ortho and para center. So electron density is rich in the meta center. Meta center is rich in electron density. So obviously, whenever the electron density is pulling the electrophile towards itself, so what we are getting? The electrophile gets attached and the carbocation is formed here. Done. So this will be relatively more stable carbocation as it gives further the product formation. Fine. So out of the other two, carbocation will be more stable in this case. What are the factor? Resonance, that is canonical structure of the nitrobenzene. If you see, with that, if you do electrophilic substitution reaction, with that we get this carbocation. So this is the stabilizing factor of carbocation. My answer will be D. Done. Not this one. Okay. Which of the following is correct with respect to minus I effect? With respect to minus I effect, which of the following is correct? Now, what is minus I effect? This is the shift of electron density. This is the shift of electron density with respect to electronegativity. Okay, so electronegativity plays the role in the shift of the electron. So minus I effect means electron is being withdrawn. What are the groups present? We have fluorine, we have oxygen, and we have nitrogen. Nitrogen from NH2, oxygen for OR, and we have F, right? Electronegativity order, if I see, fluorine is more electronegative than oxygen than nitrogen. This is the order of electronegativity we know. So according to the order of electronegativity only, my minus I effect will work. So minus I effect of fluorine will be more than OR than NH2. For 16, the answer is A. 17. What is the correct order of decreasing stability of the following cations? Order of decreasing stability. So we need to check the stability for the cations which are given here. What is the factor leading to the stability? Here, what factor is working? Resonance. Sorry. The factor which is working here is hyperconjugation. So how many hyperconjugative structure is possible here? 3 plus 3. 6 hyperconjugative structure is possible. Fine. In the next case, here we see hyperconjugation. So how many? 3 hyperconjugation plus we have lone pair of electron on oxygen which participates in the resonance. So we have a resonance effect also in the second case. Hyperconjugation plus resonance. In the third case, what are the factors working? 3 hyperconjugation, 2 hyperconjugation. So total hyperconjugation structure is 5. Right? If I have to see priority, I'll give more importance then to aromaticity. Then I'll give importance to resonance. Then I'll give importance to hyperconjugation. And then I'll give importance to inductive effect. So this is my criteria of choosing whether I'll give priority to which of the following conditions. Aromaticity first, then resonance, then hyperconjugation, and then inductive effect. So if you see, obviously resonance is coming here. So this will be more stable. This will gain extra stability. Next, 6 hyperconjugative structure gets stability over 5. So my thing should be 2 over 1 over 3. This should be the thing. So 2, 1, 3 is present in option A. 17 option should be A. Okay. This priority happens in most of the cases. Next, question number 18. Consider the following compounds. Okay, these are the compounds given. Hyperconjugation occurs in. We have to check where hyperconjugation is occurring. Okay, now for hyperconjugation, we need alpha hydrogen, presence of at least one alpha hydrogen, and the alpha carbon should be sp3 hybridized. These are the two conditions at least we need for hyperconjugation to happen. Fine. With respect to this particular free radical, what is the alpha carbon? This is alpha carbon. This is the alpha carbon. Can you see any alpha hydrogens? In this case, there is no alpha hydrogen present. If no alpha hydrogen is present, means it will not show hyperconjugation. Done. In the next case, we have this free radical, alpha carbons. What are the alpha carbons present? Phenyl. These are phenyl groups. Phenyl means what? Benzene ring. So if you see the structure, actually this is phenyl group, na? This is the structure. 3 phenyl groups are present. Now, this is the alpha carbon. Can you see any alpha hydrogens present here? No. Also, these are sp2 hybridized. So, this will also not show any hyperconjugative structure. For the other one, if you see the free radical present here, what is the alpha carbon? This one and this one. I'll not see this, as this is a bridgehead. It takes a different type of rule. So, we are not learning it. We'll not see this. This alpha carbon contains one hydrogen. So, alpha hydrogen is present here. We have a sp3 hybridized alpha carbon along with alpha hydrogen. So, both the conditions are being satisfied for the third case. So, 3 will definitely show hyperconjugation. My answer will be B, 3 only. Done. Next one. Which of the following carboxylate ion is more stable? So, stability of carboxylate ion we need to check. If you see carboxylate ion has electron density on it. Carboxylate ion has electron density. To make it stabilize, the groups must be attached such that it pulls the electron density away from it. Then only it will become stabilized. Already electron rich, right? Already electron rich. So, we have to put a group which withdraws the electron density, which will act in the stabilizing factor. Methyl group, electron donating group. So, it will destabilize the system. Okay. CH2, along with that we have a Cl. Cl has a tendency to withdraw the electron density towards itself. Then we have F. This also has tendency to withdraw the electron towards itself. Then in the fourth case also we have fluorine, which are also electron withdrawing in nature. Now we know that fluorine is more strong than chlorine in minus sign, right? Then in the fourth case we have 2 fluorines. Obviously 2 fluorines being more than one than Cl. So more electron withdrawing will take place in the fourth case in comparison. So more stability will be gained by the D option, as 2 fluorines are present in order to withdraw the electron density towards itself. Okay, stability. 20. Which of the following represents the correct order of stability of the given carbocation? Again, we need to check the stability of the given carbocation. Carbocation means electron deficient. So, I need to put such groups which will donate electrons. So, electron donating groups must be present, right? Let's see what are the groups present around the carbocation. We have 3 fluorine. Highly destabilizes the system because it withdraws electron density. Here also we have what? Fluorine. This also withdraws the electron density, but one thing is that it is present on the alpha carbon, not directly attached to the carbocation. Here it was attached to the carbocation. So here little bit the effect is lesser than the first one. And we have hydrogen which nullifies. Okay, so high stability of the carbocation should be of CH3 plus. We have to check like that. Let's see where CH3 plus is given. Okay, CH3 plus, this is on the alpha position and this is directly. So my answer should be B for 20. Done. So we need electron donating groups, not withdrawing groups. Fluorine is a electron withdrawing group, which further destabilizes the carbocation. Next, decreasing order of stability of the following alkenes is. Fine. We need to find the decreasing order of stability of the alkenes. What factor is working here? Resonance. Resonance is working. How many resonating structure? 3. 3 resonating structure to stabilize the alkene. Okay. Here how many? 3 plus 3. 6 resonating structures. Okay. Sorry, not resonating, it's hyperconjugating structure. How many? 3 hyperconjugating structures. Here how many? 3 plus 3, that is 6 hyperconjugating structures. In which how many? 3 plus 3 and this side 3. So 9. In this how many? 12 hyperconjugative structures are present in order to stabilize. So decreasing stability will be obviously 4 more and 1 will be less. So 4, 3, 2, 1. The answer for this should be B. You know, more the number of hyperconjugative structure, more is the stability. Okay. So around the particular double bonded system, we'll check the number of hyperconjugative structures that are possible, alpha hydrogens which are present, that we will be checking. Okay, alpha hydrogens are present, so this alpha hydrogens leads to stability. Next one, the increasing order of stability of the following free radicals is. Again, what contributes to the stability? Let's check for that. This is the phenyl group which is present. Phenyl group gives a resonance stability. Fine. 3 phenyl groups, so more resonance, right? Resonance will be more than the previous case. Here 2, here 3. 2 phenyl group, 3 phenyl group, obviously more resonance. CH3, here this is hyperconjugation, right? How many? 9 hyperconjugative structures. This is also hyperconjugation. How many hyperconjugative structures are possible? 6. Right? 6 hyperconjugative structure. I told you, preference, if you have to see, aromaticity gets more preference over resonance, then hyperconjugation, then inductive. This is the criteria. So here we have only resonance and hyperconjugation. So more is the number of resonance, more will be the stability. So highest stability should be of 3 phenyl, then 2 phenyl, okay, then 3 hyperconjugation, then 2 hyperconjugation. Okay, so the answer should be B for 22. The order of stability of the following carbocations. Again, stability order we need to check. Stability of the carbocations. What is providing stability? In this particular case, this is resonance. Fine. In this case, what is providing the stability? The stability is provided by hyperconjugation. How many? 2. In this, stability is provided due to resonance. Fine. Number of resonance in benzene ring, if you see, is more than the resonance which is taking place in the straight chain. Obviously, ring stability will be more than the resonance which is taking place in the straight chain. Not 2, sorry. It should be 1, and then we'll give preference to hyperconjugation, which is the 2. Just now we have seen resonance over hyperconjugation. More number of resonance, so 3, 1 and 2. 3, 1 and 2. For 23 it is D. D should be the answer. 24. Arrange the carbanions in the order of their decreasing stability. Stability of the carbanions we need to check. What is the stability factor? Let's understand. Carbanion means electron density high. We need to put electron withdrawing groups, not donating groups. Okay. Methyl is a electron donating group. So this will lead to instability of the system. Whereas if I provide chlorine, okay, this will pull the electron density out. So this will provide stability to the system. Done. Next, again, this will provide destability, resonance. So this will provide stability. This two are stability, the remaining two are unstable. Now, see, we have phenyl. Phenyl group is providing resonance stability, that is CH2 negative. The other one which is providing stability is Cl, Cl and Cl. If you see here, number of Cl are 3. 1, 2, 3, which is withdrawing the electron density, right? Because the number of Cl is more, although here we see effect is what? Inductive, okay? Although effect is inductive, but still the number of Cl is more. 3 Cls are there to withdraw the electron density. Inductive effect here overcomes the resonance which is happening in case of the phenyl. Resonance is happening in case of phenyl, whereas inductive is happening here. Normally I told you that inductive has to be given less preference. Here I told you. But here, because number of inductive effects are more, so inductive effects become dominant over resonance. This is a very important thing. Because of the number of chlorine groups which are present, the inductive effect is dominating the resonance. If suppose I only have one chlorine, okay, one chlorine, remaining H, so that time inductive effect will not dominate. As the number of chlorine increases, only then inductive effect dominates. This is an important question, right? So here what I'll get, this will have the highest stability, then the resonance, then we have for 2 and then 3. These two are electron donating groups, so highly destabilizing. The answer for 24 should be B. 25. Select the most stable carbocation among the following. This is the carbocation, carbocation, carbocation here, carbocation here. Let's see the stability factor. For this carbocation, alpha hydrogen is present. So here what we see, hyperconjugation. In this also we see hyperconjugation. So stability is basically hyperconjugation. In this carbocation, phenyl group. So stability is due to resonance. This carbocation, stability is due to hyperconjugation. This is also stability due to hyperconjugation. We know resonance dominates hyperconjugation. So stable will be B. Resonance is the factor for stability. That too, 2 phenyl groups are present to stabilize the carbocation. Done? Okay. So today, how many topics did we discuss? We have discussed multiple topics. Isomerism. In isomerism, we have seen structural isomerism, okay, and also we have discussed questions on stereoisomerism. Structural isomerism, what have we seen? We have seen chain isomerism, questions on chain isomerism, on position isomerism. We have seen questions on functional isomerism. Okay, we have seen questions on metamerism. Okay, these things we have seen from structural. In stereo, we have seen what is geometrical isomerism. We have seen what is optical isomerism question. Okay, geometrical isomerism question, optical isomerism question. In geometrical isomerism, we see cis trans type of thing we see. ZE, okay, ZE type we see. In optical, okay, in optical RS type of configuration, those type of questions we have seen. We have seen Meso compounds, okay. We have seen what are enantiomers, okay. So all these things we have covered in our question discussion. Done. These are the things that we have covered from isomerism. Then electronic displacement in the covalent bond. In electronic displacement for covalent bond that we have seen today, questions related to the topic of hyperconjugation we have seen today, resonance question we have seen today, inductive effect questions we have seen today. How all this factor provides to the stability of carbocations, carbanions, free radicals, how they provide stability. So all this we have discussed today in the question solving session. If you have any doubt, okay, you can contact us in this particular mail ID, mail us. And if you want to clarify doubt regarding any other topic for NEET 2025 or JEE 2025 that will be appeared, please mail us. We'll revert back to you. We can discuss and solve questions or any other topic discussion we can do. Fine. Thank you.